All right, so where we're going next is chapter 9, and we're going to learn some new techniques for solving differential equations using matrices. So what I want to do is I want to do a quick crash course in 2 by 2 matrices, as well as show you how the calculus of matrices would work. This video won't take very long because although linear algebra is not a prerequisite for differential equations, the majority of you are either in linear algebra or have had linear algebra. So we're going to move quickly. If you need more assistance with studying matrices, reach out to me. I can provide you with more resources, but the majority of this should come back fairly quickly. So let's begin. We'll keep it with a 2 by 2 matrix, just to keep things simple. All right. So obviously this is a 2 by 2 matrix. In other words, the dimension or the order, we'll say that this is matrix A. The order of A is 2 by 2, meaning 2 rows, 2 columns. So it's important when you're discussing a matrix to always list rows by columns. So the dimension of the order is always rows by columns. Okay, now a square matrix, or actually let's start with the elements of a matrix. So for example, in this 2 by 2 matrix, A, B, C, D, these are elements of the matrix. So for example, let's do B. B is an element of matrix A, and B is located at what you would say is it's located at the following position. So this would be B is located at row 1, column 2. So the way you would write that is A with a subscript 1, 2, meaning row 1, column 2, and then you would say that that is equal to B. All right, now a square matrix is fairly simple. What we have above is a square matrix. It's a 2 by 2. But anytime your rows are equal to your columns, what they would call an n by n matrix, you have a square matrix, so a 3 by 3 or a 4 by 4, so forth. Now, the vectors, we can think about vectors being columns, or we can think about vectors being as rows. But for example, for a column vector would mean it's a 1 by n matrix, right? Or actually, since we're doing that's a row vector. Now that I think about it, so a column vector would be a n by 1 matrix. So n by 1 meaning n rows with 1 column. This would be, I'll give you an example here. This would be a column vector. So for example, AC would be a column vector. Row vectors are just the opposite. It would just be a 1 by n. So you think of the vector, say, AB as a row vector. All right. Now the identity matrix, again, just sticking with the context of a 2 by 2 matrix, an identity matrix, what we label I, is the equivalent of how you would write the number 1, only it's the matrix analog for the number 1. And in this case, for a 2 by 2 matrix, it would be written as follows. So any matrix out there, including matrix A, any matrix times the identity matrix will equal itself. So A times I, or I times A, will equal A itself, because just like any number times 1 would be itself. All right, now the zero matrix is very simple. It's for a 2 by 2. It's just going to be all zeros as its elements. The context of a zero matrix matters, of course. If you were dealing with a 3 by 3, then this is what the zero matrix would look like in a 3 by 3 matrix. So the context matters because we'd have to know exactly what type of matrix, when we say zero matrix, what it is that we're discussing. Now, when you're adding or subtracting matrices, let me see if I can actually move this down a little bit. Yeah. So when you're adding, subtracting matrices, the condition is that it must have the same dimension, the same order. So you can add a 2 by 2 to another 2 by 2 matrix, and it's fairly simple. I'll just go ahead and make up something. So for example, 2, 3, 4, 5, if you were to add that to matrix 1, 5, 1, 1, let's call this matrix B. Let's call this matrix C. So in order to say, if you were to ask to find B plus C, once you have determined that they're both 2 by 2 matrices, then you can proceed to add or subtract, and you would just simply add each corresponding entry. So it would be 2 plus 1 is 3, and then 3 plus 5 is 8, and then 4 plus 1 is 5, and then 1 plus 5 is 6. So this would be a new matrix, and it would be the matrix B plus C. Matrices are commutative in the sense that when it comes to addition and subtraction. So B plus C would be the same as C plus B. That's not the case when it comes to multiplication. But before we tackle multiplication, let's go ahead and tackle scaling. So I'll just go ahead and borrow matrix B. So if you wanted to take matrix B and scale it by 5, then the result would be the same as taking each entry in B and scaling each entry by 5, right? So the result is simply going to be 10, what do we got, 15, 20, 25. So that's how we scale a matrix. Now, the multiplication of matrices it is different than addition. It's not this, you don't multiply the corresponding entries. So for example, if you wanted to, and I'll just go ahead and say, let's let A, B, C, D, we'll use A. And then we'll have some, so this is matrix A, and then we'll have some other 2 by 2 matrix, let's say, I don't know, E, F, G, H. And we'll say that this is matrix B. Okay, so if you were to multiply A times B, well, first let's identify the conditions that have to be met. Well, they do have to. So the best way to look at it is, so this is a 2 by 2, this is a 2 by 2. These entries right here have to be equal to each other in order to be able to multiply a matrix. So they don't have to be the same order, right? I'm going to erase this, but if you had a 2 by 3 and you wanted to multiply that by, I'm going to use a dot instead of the X. So if you wanted to multiply a 2 by 3 matrix with a 3 by 5 matrix, although the dimensions are clearly different, I mean they would look massively different. But so you got the number of columns for the first matrix has to match the number of rows for the second matrix. And if you do, then structurally you have the ability to multiply the two matrices. The outcome of what you would expect to get when everything's said and done is actually a 2 by 5 matrix. So when everything's said and done, in other words, to make sure you understand, these have to match in order to multiply. Once you have determined that structurally you can multiply, then the result of the multiplication is a 2 by 5 matrix. Now, again, how we multiply A times B is, well, just to make sure you understand, it didn't have to be this way. We normally in mathematics, you start with a goal, and then you manipulate your rules in order to reach your goal, and then the only thing that we request from our axioms, from our definitions, from our rules, is that they don't lead to contradictions from previous axioms, right? So they can't contradict any previous axioms. But the idea for multiplication is you multiply rows by columns. Okay, so I'm going to show you what the result of this would look like. So you would take row 1 for the first matrix and multiply it by column 1. Now, do you understand that what I have circled, what I have boxed in here, that would be the very first entry of the matrix? Okay, so it's row by column. So when we do this row by column, this would be A times E plus, and then we would have B times G. All right, so that, whatever A, E, B, G, whatever that is, once you multiply and add, that would be the first entry. All right, and then what we can do is we can do row 1 by column 2. So in that case, we would have A, F plus B times H. And then you just proceed in this fashion. Now it would be row 2 times column 1. All right, I'm just going to fill in the rest of it. So C, E plus D, G. And then finally, the row 2, column 2 would be C, F plus D, H. Okay, so notice that the result is a 2 by 2 matrix. And that is exactly like what I was saying earlier. The result will always match the structure of that I'm circling right now. So, okay, so that is some basics. Now, if you wanted to do, just to make sure you understand that A times B will almost never equal B times A, right? So, there's only a very specific situation where A times B would equal B times A, and that's if you're dealing with inverse matrices, which we'll discuss in just a second. But just because of the way we have structured multiplication, you're just, which is odd, and normally 2 times 3 is equal to 3 times 2, that commutativity is just not there when we do matrix multiplication. All right, now, a determinant, without really elaborating on what all a determinant can do, as of now, let's just state that a determinant can tell you if the matrix is invertible, right? It can tell us if matrix is invertible. All right, can you actually take the inverse? So I'll do two things at one time. So let me start with the inverse of the 2 by 2 matrix, right? So this would be so the inverse of a 2 by 2 matrix. Again, if we use matrix A, which was A, B, C, D, then A inverse looks like the following. It would be 1 over A times D minus B times C, and then that 1 over that is actually what we call the determinant, is then scaled to D, say negative B negative C A. All right, so if matrix A can be inverted, right, then this is how you would do the inverse of a 2 by 2 matrix. Now, what the way that the determinant can help you figure out if the matrix has an inverse is notice that this portion right here, A times D minus B times C, cannot be 0, right? Because you would be dividing by 0 at that point. So that it's really the determinant that's multiplied to this matrix here. So we have A, D minus B, C is the way we can define our determinant, right? So we're working with 2 by 2 matrices. And if this, let me go ahead and say, so if this equals 0, then there is no inverse. Okay, if A times D minus B times C does not equal 0, then we have an inverse. Okay, now while we're here, we may as well say that if you were to take 3 and multiply it by its multiplicative inverse, 1/3, right? 3 times 1/3, you would get 1. Any matrix multiplied by its inverse will also give you 1, only it would be the identity matrix. All right, now to transpose a matrix is simple enough. It just, I don't know that I even need to show you. To transpose just means the columns will become the rows and the rows will become the columns. So, right, so it's just a matter of you switch the columns and the rows. So if I were, again, using matrix A, which is A, B, C, D, right, so if this is A, then A transpose, so that's A, so then A transpose, now what's going to happen here is the row, you can say the rows or the columns are going to end up becoming, so the columns of matrix A will become the rows of A transpose. All right, so here's the column of matrix A, AC. That's a column, so that will become, that's the first column, so that will become the first row. Likewise, BD is the second column, so that will end up becoming the second row. Okay. Now, other things that I'm not going to cover in detail is the fact that you know how to row reduce a matrix, right? RREF or REF. If this is something that you either don't remember, you might have to do a quick YouTube video on it, on how to row reduce a matrix. And then, of course, your calculator can do a lot of that heavy lifting for you. But what I want to do now is I want to show you how many of these techniques apply, even if you're doing calculus of matrices. So let's let the following be our matrix. Okay? And notice now, so instead of being matrix A, it's matrix A of T. Right, because now each entry is somehow a function of T. So, really quickly, the derivative A prime of T is fairly straightforward. You would just simply go through and take the derivative of each entry with respect to T. So, A prime of T would, let's go with entry by entry, so this would be 2T. And the derivative of cosine is negative sine of t. And the derivative of e to the t is still e to the t. And of course, the derivative of 1 is 0. If you wanted to do definite integration, just as easily. So what you would do is you would start off, you would integrate each entry. So that's what I'm going to do right now. So if you integrated so this what you're integrating with respect to t. So well, I tell you what, let me do it this way. So let me, this is, I'm all on my only pause here is I'm using a different, I'm using a different matrix. So let me just give you a different matrix here. So let's say b of t is equal to the following. So let's say it's equal to t cubed over 3 plus t. And then we got sine of t. Then we have e to the t. And then we have t. And now, what if you wanted to integrate b of t? So let's go ahead and do that right now. Not that we couldn't have done it with a. It's just it's good to have some different exposures to some different problems anyway. So let's go ahead and proceed. So we're going to integrate each entry. So in this case, yeah, actually, now I know exactly what I did. Yeah, I did. I on my paper. Let me show you what I've done in my haste. I thought I wrote a different matrix and then inverted a different matrix, but I did not. So I did indeed what I was correct in my first assumption, that I integrated a of t. So all right, so now starting with a of t, so if you integrate t squared plus 1, you do get t cubed over 3 plus t. If you integrate cosine, you get sine. If you integrate e to the t, you get e to the t. If you integrate 1, you get t. So my initial thought was correct, just my handwriting somewhat sloppy. Now, just like since it's definite integration, we always are going to end up back substituting here for our upper and lower bounds. And that's really what's happening right now. So what you would get when all is said and done, so now you can think of it as a of 1. I'll write it as the way that you're used to. So write it as f of 1 minus f of 0 is what I'm doing right now. Only we used a notation instead of f notation. So we end up with 4/3. Then we end up with e minus 1. And then 1 here, and then we have sine of 1 minus sine of 0, so that's just sine of 1. Okay, so we're going to conclude this video. Again, this was, I went pretty quickly, but this was just a crash course in 2x2 matrices with the minor addition of, so looked at how we do some calculus with some matrices that'll come up in just a little bit. But when we get back, what we're going to do, in the next video, we're going to start the real chapter 9. And the goal is to, again, we're solving systems, but now we're going to see how matrices can aid us in the solution process. I'll see you soon.